54-ാം സംസ്ഥാന വാർഷികത്തിന് എത്തിച്ചേർന്ന എല്ലാ പ്രതിനിധികൾക്കും പരിഷത്ത് സുഹൃത്തുക്കൾക്കും അഭിവാദ്യങ്ങൾ. നമ്മുടെ ഈ സമ്മേളനം ഇന്ന് ഉദ്ഘാടനം ചെയ്യാൻ എത്തിയിട്ടുള്ളത് ഇന്ത്യയിലെ അറിയപ്പെടുന്ന വളരെ മുൻനിര ശാസ്ത്രജ്ഞനായിട്ടുള്ള പ്രൊഫസർ പി ബലറാം അവർകളാണ്. അദ്ദേഹം പൂനെയിലെ ഫെർഗുസൺ കോളേജിൽ നിന്ന് ബിരുദവും IIT കാൺപൂരിൽ നിന്ന് ബിരുദാനന്ദ ബിരുദവും അതിനുശേഷം US വെച്ച് അമേരിക്കയിലെ കാർണഗി യൂണിവേഴ്സിറ്റിയിൽ നിന്ന് ഡോക്ടറേറ്റും എടുത്ത വ്യക്തിയാണ്. കെമിസ്ട്രി ആയിരുന്നു അദ്ദേഹത്തിൻ്റെ ആദ്യ വിഷയം. അതിനുശേഷം പോസ്റ്റ് ഡോക്ടറൽ ഫെലോഷിപ്പായിട്ട് ഇത് ലോകത്തിലെ തന്നെ ഏറ്റവും അറിയപ്പെടുന്ന ഓർഗാനിക് കെമിസ്റ്റുകളിൽ ഒരാളായിട്ടുള്ള റോബർട്ട് വുഡ്വേർഡ് എന്ന വളരെ പ്രസിദ്ധനായിട്ടുള്ള ശാസ്ത്രജ്ഞൻ, നൊബൽ സമ്മാനം നേടിയിട്ടുള്ള വുഡ്വേർഡിൻ്റെ കൂടെ പ്രവർത്തിച്ചിട്ടുണ്ട്. അതിനുശേഷം ഇന്ത്യൻ ഇൻസ്റ്റിറ്റ്യൂട്ട് ഓഫ് സയൻസ് ബാംഗ്ലൂരിൽ ആണ് ദീർഘനാൾ അദ്ദേഹം പ്രവർത്തിച്ചിട്ടുള്ളത്. നമ്മൾ പ്രത്യേകിച്ചും ബയോളജി മേഖലയിൽ ആണ് പ്രവർത്തിച്ചത്. സ്ട്രക്ചറൽ ബയോളജി എന്ന് പറഞ്ഞ മേഖലയിലാണ്. നമ്മളെപ്പോഴും ബയോളജിയെ പറ്റി ആലോചിക്കുമ്പോൾ ആദ്യം മനസ്സിൽ വരുന്നത് എല്ലാവർക്കും DNA പറ്റിയാണ് എല്ലാവരും അറിയുന്നത്. DNA ജനറ്റിക് കോഡും ഇതുമെല്ലാമാണ്. എന്നാൽ ഇന്ന് ഏറ്റവും കൂടുതൽ പഠനങ്ങൾ നടക്കുന്നത്, ബയോളജിയിലുള്ള പഠനങ്ങൾ നടക്കുന്നത് പ്രോട്ടീനുകളുടെ മേഖലയിലാണ്. പ്രോട്ടീനുകളാണ് നമ്മുടെ എല്ലാ ജീവിവർഗങ്ങളും തമ്മിലുള്ള വ്യത്യാസം. എല്ലാവിധ ജൈവ പ്രവർത്തനങ്ങളും നടക്കുന്നത് പ്രോട്ടീൻസാണ്. ആ പ്രോട്ടീനുകളുടെ ആകൃതി അനുസരിച്ചാണ് ഓരോ പ്രോട്ടീനും ഫങ്ഷൻ ചെയ്യുന്നത്. ഓരോ എൻസൈമും എല്ലാം അതിൻ്റെ ആകൃതിയാണ്. പ്രൊഫസർ ബൽറാമിൻ്റെ ലബോറട്ടറിയിൽ നടക്കുന്ന പ്രവർത്തനം പ്രധാനമായും പ്രോട്ടീനിൻ്റെ ചെറിയ ചെറിയ ഘടകങ്ങളായിട്ടുള്ള പെപ്റ്റൈഡുകൾ, ആ പെപ്റ്റൈഡുകളുടെ സ്ട്രക്ചർ അതിനെപ്പറ്റിയുള്ള പഠനങ്ങളിലാണ് അത്തരം ശ്രദ്ധ കേന്ദ്രീകരിച്ചിട്ടുള്ളത്. അതുതന്നെ ഇന്ന് നമുക്ക് എല്ലാവരും MRI സ്കാൻ എല്ലാം കേട്ടിട്ടുണ്ട്. MRI സ്കാൻ ചെയ്യുന്ന ന്യൂക്ലിയർ മാഗ്നറ്റിക് റെസണൻസ് എന്ന് പറഞ്ഞാൽ NMR ഉപയോഗിച്ചുകൊണ്ട് പ്രോട്ടീൻ്റെ സ്ട്രക്ചർ നോക്കാൻ, അല്ലെങ്കിൽ ക്രിസ്റ്റലോഗ്രാഫി ഉപയോഗിച്ചുകൊണ്ട് ഒക്കെയുള്ള പ്രോട്ടീൻ സ്ട്രക്ചർ, ഇത് വളരെ വളരെ പ്രധാനപ്പെട്ട പുതിയ മരുന്നുകൾ കണ്ടുപിടിക്കുന്നതിലടക്കമുള്ള എല്ലാ കാര്യങ്ങളിലും അടിസ്ഥാനപരമായിട്ടുള്ള പ്രവർത്തനങ്ങളാണ്. അപ്പോൾ ആ വളരെ അടിസ്ഥാന മേഖലയിൽ ഇന്ത്യയിൽ നിന്നുകൊണ്ട്, പൂർണ്ണകാലം ഇന്ത്യയിൽ നിന്നുകൊണ്ട് തന്നെ വളരെ ഔന്നത്യം നേടിയിട്ടുള്ള വളരെ പ്രസിദ്ധനായിട്ടുള്ളൊരു ശാസ്ത്രജ്ഞനാണ് നമുക്കിന്നിവിടെ ഈ സമ്മേളനം ഉദ്ഘാടനം ചെയ്യാൻ വന്നിട്ടുള്ളത്. ഇതുകൂടാതെ അദ്ദേഹം വളരെ ഭംഗിയായിട്ട് തന്നെ ഒരു സയൻസിനെ പറ്റി എഴുതുന്ന വ്യക്തി കൂടിയാണ്. ദീർഘനാൾ അദ്ദേഹം ഇന്ത്യൻ ഇൻസ്റ്റിറ്റ്യൂട്ട് ഓഫ് സയൻസിൻ്റെ ഡയറക്ടറായിരുന്നു. കൂടാതെ കറൻറ്റ് സയൻസ് എന്ന ജേർണലിൻ്റെ എഡിറ്റർ കൂടിയായിരുന്നു. ആ കറൻറ്റ് സയൻസ് എന്ന ജേർണലിൻ്റെ എഡിറ്റർ എന്ന നിലയിൽ അദ്ദേഹത്തിൻ്റെ എഡിറ്റോറിയലുകൾ അത് ഓരോന്നും വളരെ കൃത്യമായി, പോപ്പുലർ സയൻസ് താല്പര്യമുള്ളവരെല്ലാം കറൻറ്റ് സയൻസിൻ്റെ വെബ്സൈറ്റിൽ പോയി കഴിഞ്ഞാൽ ആർക്കൈവ്സിൽ നിന്ന് എല്ലാ എഡിറ്റോറിയലും കിട്ടും. അത് വായിച്ചിരിക്കേണ്ടതാണ്. അത്ര ഭംഗിയായിട്ട്, ഞാനൊക്കെ പ്രൊഫസർ ബലറാമിനെ ആദ്യം കേൾക്കുന്നത് തന്നെ കറൻറ്റ് സയൻസിൻ്റെ എഡിറ്റോറിയലുകൾ വായിച്ചിട്ടാണ്. അദ്ദേഹത്തെ വളരെ സന്തോഷപൂർവ്വം ഞാൻ ഈ സമ്മേളനം ഉദ്ഘാടനം ചെയ്യാൻ വേണ്ടി ക്ഷണിക്കുകയാണ്. Professor Balram, I very respectfully invite you to inaugurate the 54th annual conference of KSSP.
And I will tell you a secret as to why I immediately agreed to come to the conference. The reason is that two of my very close friends have always been associated with the organization and have participated in many of its events. One is my old friend Professor R.V.G. Menon, and the other is my close colleague of many, many years, Professor M. Vijayan, who is my senior colleague in Bangalore. When I received the invitation, I was given a task, and the task I will read to you. It's very dangerous to accept invitations to speak when the organizers tell you what you should speak about. The organizers, Professor Arvind wrote me a very nice email. He said, you can speak on whatever you like, but the audience would like to listen to the current status, potential, and future of science as it is practiced in India. This is a very difficult task. It's extremely hazardous to predict the future. What one can do about the future is to extrapolate from the present. But this, of course, is very dangerous in science. It is very dangerous in human affairs because many things happen which make all your extrapolations look meaningless. The second problem is it's very difficult to understand the present. We all live in the present. We find it very difficult to understand why we are the way we are and why is our country and our surroundings the way it is. To understand the present, we must understand the past. And therefore, some of what I will say at the beginning will deal with the past of science. Because this is a meeting which is devoted to the public understanding of science, to the promotion of science, to the dissemination of science, I would first like to say a few words about basic sciences themselves. How does science actually advance? How does science progress? Now, there are two ways in which modern science has progressed, and this is the way even ancient science progressed many, many hundreds of years ago. The first is the process of observation and classification. You need to observe nature around you, and afterwards you need to classify your observations to make an integrated synthesis of what you have found. I will give you only examples from 19th century science. The most dramatic examples of observation and classification are the observations made by Charles Darwin and the subsequent classifications which he then achieved. This really laid the foundations of biology in introducing the principle of natural selection, of variation, of adaptation. So biology is deeply rooted in the 19th century observations of Darwin. Chemistry, the subject which I have studied, is deeply rooted in the periodic table. So if you go to any chemistry laboratory, you will find that the periodic table hangs on the walls. And today, not even the students look at the periodic table. In fact, the very idea of the word chemical in the popular discourse is today distorted. When you advertise saying that you're selling a product which is organic in nature and which is chemical free, what you're actually doing is you're telling the public a lie. Today you will find many, many products, some of them famous products, some of them traditional products, being sold with the advertisement that they are chemical free. We must remember that nothing is chemical free. You are only bags of chemicals. Everything is around you is chemicals. And the earth itself is chemical in nature. And the elements, the identification, the classification of the elements all began with Mendeleev's observations in the 19th century. This is probably one of the most remarkable syntheses of observations which have been made, catalogued the observations, organized the observations, and then eventually he had a periodic table which had many gaps in it. The moment this was done, other people could find new elements and fill the gap. All the new elements that have been found in the days after Mendeleev are the very elements that are driving science and technology today. The most common object that you see today, the cell phone, one of the most advanced pieces of technology that we have, of communication technology that we have today, would not work without the lithium battery. It would not work without many other elements which are found in it, in the electronics which are found in it. You need metals like gallium, you need metals like indium, and every time you hear about this, you realize how important the 19th century work of Mendeleev was in actually producing the periodic table for us. there are also practical reasons why we must understand this kind of science. The reason we must understand is when we look at Mendelev's periodic table, we will find that there are so many elements. The next question is, are these elements useful? Many of the elements are very useful in technology. We don't have to worry about the elements which are useful in biology, because biology takes care of itself. Most of us can go through life without knowing anything about the biology which makes us tick. On the other hand, for technology, you need to understand what you need. Today, for example, most of the elements which are needed for technology are not available in India. They are not mined in India. There is no uranium for nuclear purposes. There is no gallium. There is no indium. You can hardly find any copper. There is no lithium. And it turns out that the sources of all the rare earths, all of them are really coming today from China. Therefore, it is of great importance that governments, policymakers, and general public actually understand the importance of chemistry, of the importance of elements, what are the critical elements that one needs for technological processes, where are we going to get them. Today, in my own state where I have lived for so many years, Karnataka, mining is a very bad word, because mining is associated with politicians, and almost anything which is associated with politicians eventually gets a bad connotation, irrespective of their ideology. Why are people against mining? People are against mining because of environmental depredations. But it turns out that mining is also an essential activity. So there must be in our balance in our approach to science, in our balance in our approach to technology, and we must have a clear idea of what our strategic interests are, and we cannot have a clear idea of what our strategic interests are unless we have a clear idea of the underlying science. So observation and classification are important. But observation and classification have always been important. What were the ancient scientists able to observe? They had no light around them. There was no electricity. Edison was many centuries into the future. And therefore, what did Aryabhatta and others have to observe? All they had to observe were the skies. And when you observe the skies at night, without any background illumination at all, we can't observe the skies anymore with our naked eyes, because there's so much light now coming from the ground. You see the stars, you see the planets. And therefore, one of the earliest disciplines to have been born, and I must say this with Professor Chatterjee here in the audience, really was astronomy. And this is why, when you look at the motions of the planets and so forth, astronomy and to a great extent astrology were born at the same time. And therefore there has always been this confusion of which is a science and which really has become a part of human culture, sometimes associated with superstition and sometimes having no hard scientific basis. But one can understand how these things have actually developed. The second way of actually doing science is to do an experiment, make an observation, and based on the observation, give an explanation. I will take another example of 19th century science. I think if you go to a science exhibition today in school, there is one experiment which will be demonstrated by the overwhelming majority of students who are there. And that is an old experiment done by Michael Faraday, where you show that if you have a current flowing in a circular coil, it will in fact deflect a magnet which is close by. And the second is, of course, if you have a rotating magnet, you can generate now a current in a circular coil which is placed. So what did this experiment show? It showed a connection between electricity and magnetism. It also introduced the principle of electromagnetic induction, which is at the heart of much of power generation in later years. When Faraday first did this experiment, everybody liked it. And I will tell you one story here, because it is a story which I found that even the current president of the Royal Society, Professor Venki Ramakrishnan, had not heard of. You can ask a question to a general audience. Which is the first one-way street in the world? Today, when I was driving into Kannur yesterday, I found that even Kannur has one-way streets. Bangalore has only one-way streets. And which is the first one-way street in the world? It turns out that the first one-way street in the world is the street in front of the Royal Institution in London. And why did it become a one-way street? Because in the Victorian era, Michael Faraday used to do experiments when he was talking to the general public at the Royal Institution. And his audience was entirely composed of Victorian ladies who would come to watch these wonderful experimental demonstrations which Faraday would do. And the ladies in Victorian times would not walk. They would come in horse-drawn carriages, and the carriages would be parked right in front of the Royal Institution, and therefore after some time the traffic could move only in one way. So the English, with their characteristic pragmatism, then invented the concept of the one-way street. But the first traffic jam in the world really has been caused by scientific demonstrations of Michael Faraday. So you can immediately see the kind of interest that the general public can have in science and in the kinds of phenomena that are actually observed. But the connection between electricity and magnetism really requires very much more than experiment. It requires thinking, it requires theory, and this had to wait. The Scotsman James Clerk Maxwell, who introduced then really the theoretical underpinning, in fact what you might call the first grand unification in physics, which unified electricity and magnetism. And out of Maxwell's unification really came something remarkable. The light photon simply emerged. And what you can really say here is, in one stroke, Maxwell unified what we commonly knew at that time. He unified light, he unified electricity and magnetism. Almost, I would say, 100 years after all of this, when I studied physics in the Ferguson College in Pune, we still were taught electricity separately, magnetism separately, and we were hardly taught anything about spectroscopy, which uses light. But today, these are things which I think students must learn right at the beginning and understand the unity of many of the things that are actually noticed. I'll come to a later time, but before I come to a later time, I must say one thing. Today, there is a great deal of talk about what was known about science 1,000 years ago, 2,000 years ago, 3,000 years ago, or even 700 or 800 years ago. What you observe depends on the tools that you have to observe. What was the tool which really transformed our understanding of the universe, of the role of the earth as one of the objects in the universe? It was the invention of the telescope. And it's really when Galileo turned the telescope towards the heavens that astronomy was really born. Subsequently, telescopes have become much more powerful. There are all kinds of telescopes which use other parts of the electromagnetic spectrum. And therefore, we observe a great deal more about the planetary system, about the universe, and therefore you have entire fields which are devoted to their understanding. In the field that I practice today, biology, most of the living organisms on Earth cannot be seen. And if you ask me what was the most important development in allowing us to see what we cannot see with our eyes, it was the invention of the microscope. It was only when the microscope was invented in Holland and Van Leeuwenhoek began to look at water contaminated water that he saw bacteria. Now we know the largest group of living organisms on earth are organisms that you cannot see. So when you have, and I asked this question yesterday to students at the university in Kannur, when I was talking to them about biology, I asked them this question: how many living organisms are there on earth? I did not get an answer, I did not get an estimate, because anybody can give any estimate, there is no way of checking. At the same time, I asked them, how many of you are interested in working for NGOs that are protecting biodiversity? A few hands went up. Now, if you're interested in protecting biodiversity, it is very important that you first educate yourself on all the biodiversity that actually exists on the planet. There will be plant diversity, there will be animal diversity, there will be microbial diversity. And it turns out that biology in the form of microbes and microbial life will long outlive human beings. And this is in fact a sobering thought. If there is one thing that science teaches you, whether you use the telescopes or whether you use the microscopes, it is that you see wonderful things. And when you see these wonderful things, what you develop is a great sense of humility about your understanding of the world around you. The most important quality that science should teach a student is the quality of humility. And one is in fact humble before nature. But the world around us, the scientific world around us, has been shaped by two revolutions. Both of these revolutions happened in the 20th century. The first, in the first half of the 20th century, that's the revolution in physics. The revolution in atomic physics, the appearance of quantum mechanics, and eventually leading up to the Second World War with the exploding of the first atomic bomb. This then told you what the power of the atom was, what the power of the atomic nucleus was. But immediately after this, in the early 1950s, Watson and Crick discovered the double helical structure of DNA. This immediately connected two subjects. This connected the classical genetics of Gregor Mendel, and it connected it to chemistry, the chemistry of heredity. We now began to know about genes. We began to get the connections between genes and disease. And towards the end of the 20th century, the advances in sequencing technologies allow us now to determine sequences of entire genomes, genomes of organisms, genomes of human beings. And therefore, there is a clear connection now between genetics, disease, and the potential of all these new methodologies in the detection and maybe sometimes therapeutic interventions in disease in the future. But it turns out that the biological revolution was accompanied by a revolution in the analysis of chemical molecules, molecules of increasing complexity, proteins, nucleic acids. Where did the tools for this analysis come from? The tools for this analysis came from physics. Even though I do not understand Malayalam, I realized that when Professor Arvind was talking, he did mention nuclear magnetic resonance, he mentioned magnetic resonance imaging. It turns out that the origins of magnetic resonance imaging can be traced back to the early 1940s, when Rabi, a physicist at Columbia University, actually determined the magnetic moment of the atomic nucleus. And it's Rabi's molecular beam experiments, an esoteric experiment in physics, which eventually gave rise to the technique of nuclear magnetic resonance, which in later years gave rise to magnetic resonance imaging. So today, a technique which started in physics has now ended in medicine. Therefore, today's general public, today's students must all have a broad understanding of the interdisciplinarity of modern science. It is not enough to study physics, it's not enough to study chemistry, it's not enough to study biology. You must know a little bit of each of these, and you must have a little bit of mathematics thrown in, and most importantly, a familiarity with modern computing methods and computers. So you need to know a great deal. And therefore, I turned then to the subject that has really been allotted to me. And that is the subject of our own country, India. Now, when I talk about science in India, its past, its present, and possibly its future, my evaluation of the way things have happened must necessarily be a prejudiced one. It can only be a personal opinion, but I will nevertheless tell you a little bit about this. What is the past of Indian science? The past of Indian science, and I do not mean the science of the very old days, I do not mean the ancient Indian astronomers, not the ancient Indian mathematicians, but the science really of the 20th century. There was, of course, what one may call the Kolkata, or in those days under the British, the Calcutta phenomenon, and that was in the first 2 to 3 decades of the 20th century. Just imagine the city of Calcutta in the 1920s. At one time, in one decade, in the same city, there was Rabindranath Tagore on one side, Jagdish Chandra Bose on the other, both actually contemporaries. There was another contemporary, a great contemporary of theirs, Prafulla Chandra Ray. He's the founding father of modern chemistry in India. Jagdish Chandra Bose, of course, both physics and to a great extent plant physiology. And Rabindranath Tagore, of course, all of you know. The young men who came to Calcutta at that time, some of whom were educated there and some who came from outside. C.V. Raman moved to Calcutta, and it was at the Indian Association for Cultivation of Science in 1928 that he really established the Raman effect. He discovered the Raman effect. Was the Raman effect applied? Was it going to be useful? Nobody knew. It was a new phenomenon. But today the Raman effect is used even in Raman scanners, which are used for security at airports across the world. Therefore, today when governments ask you, what is the utility of science? What one can say is that fundamental science's utility cannot really be predicted at the time when the discoveries are actually made. But all these people lived at one time, and they lived in one city. It is not a city which has had a great reputation afterwards. I'm sure some of you who are older may have seen a book which appeared about Kolkata many years later, calling it the City of Joy. But it was not a very good book. It did not treat the city's past, and it did not give appropriate credit to the role that the city had in shaping modern India's science. What happened after independence? So, we can blame a lot of people for many things. We can blame the invaders who came from the north for many things that happened between, say, 1400 and maybe 1800. After 1800, we can start blaming the British for what they did between 1800 and 1947. But we might ask ourselves the question, what have we done after 1947? Now I will tell you about India's universities after independence. In the 1950s, Madras University, Calcutta University, and Delhi University were in fact great centers of learning. So was Banaras, so was Allahabad. Students went from Kerala to study in Banaras and Allahabad. Professor Vijayan himself has always told me stories of going from Kerala to study for a master's degree at Allahabad University. Students went there. These were universities which were in fact well-known universities. And the department which I joined at the Indian Institute of Science in 1973 was set up by one of the scientists who did outstanding work in post-independence India. This was G.N. Ramachandran. G.N. Ramachandran's origins are in Kerala. He was born here. He studied in Tiruchirappalli as it is called today. But later, he came to the Indian Institute of Science in Bangalore, worked with C.V. Raman, and eventually, at the young age of 29, he moved as professor of physics to Madras University. In Madras University, he did two pieces of work. One in 1954-55, when he established the structure of the major protein in our skin, collagen, and established the triple helical structure of collagen. Today, if you drive in front of Raj Bhavan and look on the other side at the Central Leather Research Institute, you will find an auditorium. It is the only auditorium that I know in India which has been named after a scientific discovery in India, and it is called the Triple Helix Auditorium. I was there for the inauguration of the Triple Helix Auditorium, then by a minister. Ramachandran was too old to go there at that time, and he was not in good health. So I was deputed to speak about his work, and the minister asked me, if this work is so important, why did this work not receive a Nobel Prize? I was somewhat younger and not so wise. I said that we should not worry about whether work done in India has received recognition by a bunch of professors sitting in Sweden. We must recognize work done in India for what it is. In the 1960s, early 1960s, 1963 to be precise, Ramachandran published another classic paper which opened up the entire field of understanding the three-dimensional structures of protein chains. These two pieces of work alone were more than enough to earn him a Nobel nomination, but he never received the Nobel Prize. But what is even more tragic is that Ramachandran died in 2002. And in 2002, when he died, he had not even been given a Padma Shri by the government of India. Those of you who know Indian political history well will know that by 2002, we had had governments in India of all possible political persuasions. We had had Congress governments, we'd had Third Front governments, we'd had NDA governments. All of them had been in power. Despite this, and despite the fact that it was over 50 years after independence that he died, he was never honored with anything really of any which brought his name to public attention. I tell you this today because one of the tasks that was given to me by the organizers was to ask whether there are instances of scientific research which can prove inspirational. Many years later, as the editor of Current Science, I came across another. This is the discovery of cholera toxin. And cholera was a disease which actually killed thousands and thousands of people in India at that time. And in the 1950s, a researcher, a medical doctor by training, a biological scientist by practice, Shambhunath Dey, working at a college which you cannot recognize today, the Nil Ratan Sarkar Medical College in Kolkata, actually discovered the principle of, he discovered cholera enterotoxin and the principle by which the bacterium secretes a toxin and results in the flow of water into the intestine, which then leads to watery diarrhea. This is a major discovery in the medical sciences because it immediately suggests that all you have to do to treat cholera is not to have a drug, not to have a vaccine, but to introduce oral rehydration therapy. So if you keep the patient hydrated by giving sufficient amount of water through the mouth, which is oral, with salts in it, the diarrhea itself will then be self-limiting. And therefore, thousands and thousands of lives have been saved. But Shambhunath Dey's work received no recognition in India whatsoever. And many years later, it received recognition in the United States when one of America's most famous scientists, Joshua Lederberg, who had won a Nobel Prize at the age of 33, wrote to Eugene Garfield to do an analysis of Shambhunath Dey's paper. It was then discovered that his paper had in fact been very important in the entire field of cholera. So in 1988, I produced a special issue of Current Science devoted to Shambhunath Dey and the discovery of cholera toxin. And when I did 2 years of research in doing this, I found that Joshua Lederberg had actually nominated Shambhunath Dey for the Nobel Prize. Dey died I think in 1987, before the special issue was produced, but he was invited to Stockholm to speak at the Nobel Foundation seminar on cholera. And he gave the post-dinner lecture, an unprepared lecture of which there is a typescript. And when you read it, you feel actually extraordinarily sad that we have been unable to recognize the wonderful work that has been done in post-independence India many, many years after independence. Therefore, when we talk about the future of India, we must understand the past and the present of science in India, the public perception of science, the political perception of science, the perception of science in bureaucratic circles, in political circles, and really by the general public themselves. What is the subject that all of us worry about? We cry month after month, year after year, government after government, about the decline of scholarship in India's universities. Universities have declined across the country, across the states, with no exception. The only solution that has been put forward is to create central institutions. And we have watched central institutions created in the 1950s and the 1960s now decline. So all this process of decline, all of us are responsible. All of us are responsible because we do not say anything about it. We do not even try to bring this to the attention of people who are in fact making policy. It is true that when we do bring this to the attention of people who make policy, they usually throw any advice that you give them into the waste paper basket. But just think about this. The current government has been producing a new education policy, and it is over 2.5 years in the making. It may be 5 years in the making. The past government produced an education policy in 1986 and modified it in 1992. I would urge you to go to the internet, look at the website and see whether you can find a copy of that document. When you look for the document, you will find an old document on which people have scribbled things. That means not even a final and original document was available to the ministry to upload on its own website. So this tells you the importance that is given to policies. Because if you read the document, you will find that you will agree with everything that is said in the document. But it will turn out that nothing which is said in the document will in fact be implemented on the ground. So we suffer not for want of policies, but really for want of political will to implement anything that needs to be actually implemented. There is also a great connection between scientific research and higher education. And by higher education, I mean education starting from college. But you also know that there's a great connection between school education and college education. Today, the syllabi, the rules which govern institutions in different states are different. But no state has a model curriculum. Children should not be asked to choose between mathematics and biology at the stage of school. Many of you will be parents, and it is sad to tell you that your children are being educated much poorer than you were educated, and you were educated much poorer than your parents were educated in this very country, in our own institutions. Yesterday, I asked the students at Kannur University, are you happy with the education system? And what was I meant? I asked the question twice, I asked the question thrice, and not a single student answered. I would have been happy if some student got up and said they're very happy with the education system, or some student got up and said they're very unhappy with the education system. But they did not even answer whether they're happy or unhappy. They were silent. And the most important thing to guard is to guard against silence when you see that things around you are not going the way they should be going. These linkages must be known. Education in India is a state subject, and therefore governments take great pride in distinguishing between the role of the center and the role of the states. Now, I noticed one thing, and I asked Professor Arvindam here. All your proceedings today are in Malayalam. It is very important to be proud of the local language. But it turns out that today, scientific discourse across the world is in English. There is no getting away from it. The French and Germans who fought the great European wars of the 20th century all now publish their journals in English. They have capitulated. This is because you need a language in which to discuss science. It has nothing to do with culture. It is not an assault on local culture. It is just a means of communication. And therefore, our approach to linguistic chauvinism must in fact undergo a change. We must be practical. What is the other problem that one can immediately see? In the approach to colleges and universities, it is governmental attitudes. Governmental attitudes can range from malignant interference to benign neglect. Sometimes I do not know which is worse. Benign neglect can be as bad as interference, because if nobody looks at you, nobody shows any interest, but pays you your salary anyway, then of course the institutions themselves slowly begin to decay at the core. I believe that over the years, Nehruvian optimism about science and nation building. Nehru once famously said that scientists are in league with the future, because future discoveries will come along and you should be able to exploit them. Atal Bihari Vajpayee, who was ideologically, I think, on a different end of the political spectrum from Jawaharlal Nehru, said something very similar. He said that scientists, and he said it in his own characteristic way, he said scientists must be in league with India's future. And that, I think, is really the purpose of meetings like this, to ask the question, how can science be used to develop local environments, more general environments, and eventually be used for India's development itself. Today, unfortunately, what we have from government is a corporate view of educational institutions. The corporate view of educational institutions is that if you invest a certain amount of money, you must get a return of investment. Now, I think this is an extraordinarily poor view of the role of education in improving the human condition. The return on investment on our public institutions really should be human capital which has been educated now. And it is those human beings who have been educated, the students of the future, who will go on to do development. There's a great need to enhance the public perception of science. The public must be able to make some kind of informed judgments on very complex issues. Today, issues of vaccines, issues of genetically modified crops, all of these are issues which must be understood in some ways because they concern you. If there is an ineffective vaccine which is introduced for a particular form of cancer, then one must worry. This has happened with the cervical cancer clinical trials which have taken place. If there is a new vaccine introduced into the childhood immunization program, one must ask, do these vaccines, are they necessary? Do they have any side effects? And so on. If we worry about genetically modified crops, we must ask, is it okay now to have recombinant crops freely grown in the fields? But I think it is the public which then needs to participate in this kind of debate. So I've really come now to more or less the concluding part of whatever I had as my inaugural remarks. I will tell you just one thing about my own institution. I have worked for 43 years at the Indian Institute of Science. And in all these 43 years, one of the most prominent scientists of the modern times from Kerala, Professor Vijayan, has been by my side. Now, this is an institution which was originally conceived in 1896. It was actually born under the British in 1909. It took 13 years of gestation for the Indian Institute of Science to be born after Jamshed Tata actually thought about a research university or a research institution in India. He called it a research university because he had a model. And the model that he had was for the first research university in the United States, which is Johns Hopkins University. Harvard and MIT became research universities much later. Stanford and Caltech very much later. So now you can see that Jamshed Tata had a very far-sighted view of what India needed for its development. And the documents that were produced are dated 1896. The British did not think very much of this idea. Lord Curzon, in his characteristic way, said that giving India a research institution at that time was like giving a naked man a top hat instead of giving him a pair of trousers. He also wanted to cut the governmental contribution to the institution. But the institute came into being really because the then Maharaja of Mysore donated the land for the institute, and at that point, two Indians, the Maharaja of Mysore, Krishna Raja Wadeyar, and Jamshed Tata, whose vision led to the birth of the Indian Institute of Science. Its first director was an Englishman who then built the structures in which we have lived and worked for so many years. But think about the Indian Institute of Science. The Indian Institute of Science, if it was born in 1909, it has survived what I would call a turbulent century. It's a turbulent century in terms of the political events that happened in that century. It began long before Mahatma Gandhi actually returned to India in 1915. By that time, the institute was already on its way. But it has survived. Today, if you read the newspapers, you will find it is the #1 ranked university in India. So we have had institutions which have managed to survive. I won't say they have done as well as they should. We should have done very much better than we have. But we have at least not decayed away. We have not decayed away like Madras University, Calcutta University, Bombay University, or Delhi University. Why has the Indian Institute of Science not decayed? And my answer to that is that the Indian Institute of Science is really one of the few institutions in India which is a truly Indian institution. The faculty are drawn from all over the country. The students are drawn from all over the country. The directors of the institution are drawn from all over the country. Nobody asks what your language is before you're appointed the director of the institution. So today, I would have only one prescription to make. I have learned never to be prescriptive, never to give advice. But I would like to say this in public because you are a public meeting with people who are concerned about science and the future of our institutions. Today, if our institutions are to make a comeback, the first thing that must be done is to try and make institutions across India, whether they belong to the states or whether they belong to the center, acquire a pan-Indian character. We must welcome students from all over India to our institutions. We must welcome faculty from all over India to our institutions. And I would say, we must adopt something that's been adopted by the judiciary. You will notice that the Chief Justice of all the states in India don't come from the states themselves. They are appointed from another state. This is to ensure a certain amount of independence of the judiciary and a certain amount of independence from local factors. How wonderful it would be if we decreed that 30 to 50% of the faculty positions in our universities across India must be really reserved for people from other states. And if we prescribed that the vice-chancellors of universities must come from another state. There is a great advantage in not understanding a local language. When you cannot understand a local language, and when you are in a position of administrative authority, and I have been in one, I can tell you that it is very advantageous because you can many times pretend that you do not understand and do not carry out instructions which you don't want to do. A certain level of independence and a certain level of distance from local dynamics and local politics will become possible only if India recognizes that it is a country and not a collection of states, each one of them celebrating their own cultures and languages. They are most welcome to celebrate their own cultures and languages. But the march of science, the march of technology, our understanding of the issues which are most important to us, agriculture, health, engineering technologies of the future, these will happen only if in fact the discourse is conducted in a language that everybody can understand and everybody can communicate. America's strength is its diversity, where it has welcomed scientists and engineers from across the world to come and work there. India has the advantage that it has huge diversity within the country itself. But we have failed to exploit this human diversity in India, and we have in fact, on the contrary, encouraged a political system which tries to segregate rather than to integrate. So there are only two morals which I would like to leave you with. Integration must be done at the level of people, and integration in teaching must be done at the level of discipline. Disciplines have also become like separate cultures. Chemists don't talk to physicists, don't talk to biologists in our universities. And students do not know the interconnections between these subjects. Therefore, we must promote integration of disciplines, and we must also promote integration of people. Finally, I would like to thank the organizers for inviting me here, for giving me an opportunity to share some of my thoughts with you, and I would like to wish all of you the very best, not only for this conference, but also in the years ahead. Thank you very much.